Hi, everyone. My name is Elton Zhu, and I lead the quantum research at Fidelity Investments. So I work in this organization called Fidelity Center for, sorry, how do I do the? Okay, so I work in this organization called Fidelity Center for Applied Technology, which is a technology incubator within Fidelity Investments. So it's a catalyst for breakthrough ideas, and we hope to bring a successful future for Fidelity and its customers. We identify and track important trends in society and computer science. We test and validate all sorts of emerging technologies, such as blockchain, AR, VR, metaverse, and quantum computing. We even have Bitcoin miners in our data center that we try to mine Bitcoins sustainably. We try to develop and bring new capabilities and products to scale. So in terms of our team, it's a very small team of researchers, software developers, security architect, product, program, and community managers. The few areas of research that we're working on is quantum system testing. Every once in a while, new providers announce new hardware or software platforms. We try to get our hands dirty. We're one of the early users of AWS Braket and IonQ system. We study quantum algorithms and see how we can integrate them into our existing business solutions. We pay very close attention to security and encryption because we want to protect our customers' data and ensure security between our data centers. Last but not least, we recognize that the quantum ecosystem is constantly changing, so we try to monitor the ecosystem very closely. We work with various internal teams in asset management. These are the people who construct mutual funds and ETFs. Personal investing, these are the business units that open for retail brokerage. Workplace investing, these are the people that offer 401k retirement planning to everyone. And last but not least, institutional investing. We talk to all these internal teams to educate them about the potential of quantum computing and find suitable use cases. In terms of the area of focus, this can be loosely defined into the following 4 tracks and the associated technology. Optimization, this is mostly related to various different types of portfolio optimization. Everyone talks about portfolio optimization. So some of the technologies that we look at include annealing, variational quantum algorithms on NISQ devices, quantum-inspired hardware and software solutions. Quantum machine learning. So machine learning is used almost everywhere in our business. So I can spend an hour talking about different use cases. Some of the techniques that we look at include quantum kernels, hybrid quantum classical neural networks. Next one, simulation. This is mostly like the simulation of the market. There are a variety of use cases here. For example, derivative pricing, retirement planning, various risk estimation, for example, value at risk, credit risk, counterparty risk. So here, the most important algorithm is the quantum Monte Carlo algorithm. Last but not least, for the security aspect, we pay very close attention to the NIST standards, and we try out the different post-quantum encryption method algorithms there, and also the quantum key distribution and some other quasi-quantum methods. In terms of research methodology, we perform rigorous benchmarking of quantum technology against the best available technology. We get our hands really dirty and challenge the technology to its limits. Now, if you offer your hardware to us, we'll send hundreds, if not thousands, of circuits just to see if you can handle the volume, and also just to see, what is the execution time and what is the queue time, and whether the computer requires recalibration and so on. We often verify the claims by external providers. For example, if a provider tells us that they have a device of quantum volume, let's say 10, we will perform our own quantum volume testing just to see whether that's true. If a provider says that we have an optimization-based solution that outperforms existing methods, we will perform our own benchmarking just to see if that's true. Sometimes we are able to verify the claims by the provider, but oftentimes we see that there's some degree of exaggeration. Sorry, how do I go back? Okay. Yeah, because the main purpose of quantum computers is to speed things up, we test if that's true based on current hardware with a reasonable projection into the future. So we have a bottom-up approach in the sense that we focus on the technology and with the use cases in mind. And we want to make sure that the technology that we look at is extendable to multiple use cases. We don't do one-time research. Last but not least, we are interested in not only how to use quantum computers, but also why. Because the main purpose of quantum computer is to speed things up. We want to see if that's true. And a lot of the complex problems can be solved by advanced AI ML-based solutions. So if there's a quantum solution, we want to understand what is the value there. Optimization. Again, just as I mentioned, this is mostly for solving various portfolio-based optimization problems. So most of the quantum optimization solvers, they solve this kind of problem called QBOS, which stands for Quadratic Unconstrained Binary Optimization Problem. That's not a problem that we're solving in our business. So we have seen ways to discretize variables to be compatible with this formalism, but we still think that there's poor support for integer and continuous variables. Most of the problems that we solve are what we call a mixed integer linear or quadratic programming. Just to give you an example in understanding this, to determine whether you want to invest in the security or not, this is a binary decision variable. And to determine how much to invest in the security, so that is a continuous variable. Actually, as of a few years ago, that is still integer, just because you can only buy security at an integer number of shares. But as the whole industry moves into fractional trading, this truly becomes a continuous variable. And also, most of the QBO-based solvers are what we call heuristic solvers, in a sense that they give you solutions, but there's no proof of optimality. The solution may be good, the solution may be bad, and you have no way to verify that. But we require something called the optimality guarantees, such as 0.1% to optimal solution, because that is the standard that we offer to our customers. So we try to benchmark these QBO solvers against the state-of-art open source or commercial mathematical programming software. So the open source solvers that we benchmark include Skip, CBC. The commercial mathematical programming software that we benchmark include some of the most advanced ones, such as Groby and Cplex. Actually, there's a bit of a challenge here because we try to benchmark the heuristic solver against a very mature mathematical programming software, and they provide optimality gaps and guarantees. So we have to purposely handicap the mathematical programming software just to be able to do a fair comparison. So we observed that there's some outperformance in terms of time to solution for quantum and quantum-inspired solvers in solving some binary quadratic problems. But for most of the problems that we look at, we haven't seen any advantage yet. Next one, machine learning. Again, this is used everywhere in our business. So here we're mostly focusing on model performance rather than speed, just because we envision the quantum speedup will come when the fault-tolerant quantum computers are available. So we frequently design and test hybrid machine learning models and benchmark them against traditional machine learning models on public and internal data sets. Some of the QML models that we have tested include quantum kernels, quantum GAN, quantum classical hybrid neural networks. So here we bring you attention to this paper that was just appears on the Physical Review Research for our work with IonQ last year. So some of the use cases include font classification, fraud detection, natural language processing, model stress testing. So we see that most of these models work, but they only work on toy data sets. And when we try them on a real-world data set, it just takes forever to run. So we think that for any of the models that are being developed, there's a need to really scale them to real-world data just to see if there's value, because ultimately we want to provide production value to our business units. Monte Carlo simulation, again, I think this is something that every financial service firm does in one way or another. So here, most of the results is based on this paper called Quantum Speedup of Monte Carlo Methods, written by Ashley Montanaro. So what it says is that it offers a quadratic speedup on fault-tolerant computers when compared against traditional Monte Carlo methods. But we became aware of this paper written by the Google Quantum AI team that says that if you take into account the clock speed of near-term device together with the cost of error correction, then the quantum advantage may not be attainable for the problem size that we're interested in. So as a result, we are also looking at higher order speedups such as cubic and quadic and also exponential speedups. So we're focusing on the resource estimation associated with any such algorithm to make sure that there's some speedup. And I'm very glad that some of the other firms are looking at it, and some of the providers, such as Microsoft Azure Quantum, they provide this resource estimation tool. And we encourage quantum providers to do similar analysis on quantum algorithms that has asymptotic speedup. In terms of hardware, so we pay attention to almost all of the hardware technologies, being superconducting qubits, ion trap, photonics, cold atom, and silicon-based computing. But we're not betting on any single technology. We try to develop quantum algorithms in a hardware-agnostic way. And we prefer the hardware with the following characteristics. So firstly, it got to be more than 30 qubits. And the reason for that is that if a quantum computer has less than 30 qubits, then it's classically simulatable. And if I have a job that has only 20 qubits, I would rather want to run on the simulator, such as a local CPU, GPU-based simulator, or some of the cloud-based simulators, because it's free, it's fast, and it doesn't have noise. Next, we also prefer the hardware to be able to execute generic short depth quantum circuits in the sense that can execute quantum gates. And we noticed that some of the hardware providers, they start providing this mode called the analog mode. We think that's very interesting, and they may be of value to some of the users. But oftentimes we see that it's really hard for us to find use cases that match directly with the feature offered by the analog mode. Last but not least, we wish the hardware to be integratable with major software libraries, such as Qiskit, PennyLane, Bracket, Cirq, and some of the new ones like Ticket and Coda. In terms of outlook, we maintain a hopeful but cautious outlook for quantum computing. And we noticed that there's a lot of hype in the industry. Some of the research work, for example, this holographic wormhole and some other papers, these are excellent academic research that is of interest to the academic community, but oftentimes they are misinterpreted by the industry or the public media. So we try to actively counter the hype internally, educating our Fidelity associates about what quantum technology can do now versus what we believe it may be able to do in the future. We find the NISQ algorithms very interesting and sometimes even very innovative, but we recognize that their value may be limited. Again, if you think otherwise, and if you have proof that a NISQ algorithm is of value, feel free to reach out to me. Last but not least, we expect more value coming from algorithms on early fault-tolerant devices. With that, I'd like to say thank you and conclude my talk.